Welcome, everyone. Good morning to you, and thank you for joining us today. My name is Kelly Timko. I'm from Galorath. I'm going to be your moderator for today's virtual Lunch and Learn. Welcome to today's Lunch and Learn. It's entitled 9 Common Mistakes that Cost Estimators Make and How to Avoid Them. We're featuring Dr. Christian Smart today. Thank you for taking time out of your busy schedule to learn something new. All lines have been placed on mute so we can avoid any background noise. If you have any questions or you need help, you can use the chat function to speak with me. Just hover your mouse over the bottom of the screen and that will appear for you. Today's training is brought to you by Galorath. Galorath is the leader in analytical program management, empowering analysts and organizational leaders to make complex business decisions with confidence through the use of predictive analytics. And of course, you can find us on the web at galorath.com. Please stick around for the live Q&A period at the end. This will be your opportunity to ask questions and make this session directly relevant to you and your organizational challenges. We'll also be providing a link in the chat window for a 2-minute post-event evaluation survey. And on Thursday of next week, we'll be giving away a $100 Amazon gift certificate from the pool of survey respondents. So please try and take a moment and check out that survey. Also, if you're from a government agency and aren't able to accept a gift certificate, we're also happy to donate that amount to a local charity if you're selected. And as well, if you know of anyone on your team right now who should be joining us this morning, you can ask them to join right now by sending them to galorath.live. That's GALORATH.live. And there are links where they can join us. As well, all the handouts from this session, a PDF version of today's PowerPoint deck, and a video of today's session when it's ready, can also be found at galorath.live. And there will actually be a total of 6 downloadable assets that will be available following today's presentation. Our next virtual Lunch and Learn will be in January. It's going to be a moderated panel discussion on project control trends and important insights for 2022. So be sure to take a moment and register for that. As soon as we have a confirmed date, we'll be able to announce that as well by email. And you can always go to galorath.live to see the latest updates. Today's training is being recorded, and it will be available for later viewing on demand. We'll be sending the URL to all the registrants by email within the next few days. Please feel free to share this video link with any of your colleagues. And let's go ahead and get started. Today's presenter is Dr. Christian Smart, Chief Scientist of Galorath Federal. Dr. Smart has 20 years of experience with cost and schedule risk analysis, predictive analytics, and probabilistic reliability analysis and machine learning. His background in aerospace includes missile defense programs, nuclear thermal propulsion, hypersonics, and robotic and crewed space vehicles. So with that, I'm going to turn the presentation over to Dr. Smart.
Hello. So I'm going to talk about 9 common mistakes that cost estimators make. And next slide here. And Kelly already told you a little bit about me. If you want to read more about me, you can see that in the slides. Let's talk about what we're going to learn today. In this webinar, you'll understand about the abuse of averages, the use and abuse of averages. It's often the case that averages are misused, and it's actually something that's pretty easy to work with, but oftentimes we use them incorrectly. Sometimes when we're using parametric equations, we misapply them. If you're in the short synopsis of that is, if you are using a CER that was developed using subsystem data, such as at the on spacecraft, if you're using it based on, say, guidance navigation control, and then you apply it to a work breakdown structure of the same system at a lower level, component level, so flight computer, et cetera, you will overestimate. We'll talk about why that is and how to fix it. Another issue is falling prey to the curse of dimensionality, which is limited data can often lead to overfitting. And even when we have a substantial amount of data, and a substantial amount of data is somewhat up for debate, if you over-optimize the training set, you still can overfit, even if you have a robust data set. So we talk about that and how to fix that. Because I'm talking about not just the mistakes, but I'm also going to talk about how to avoid it. And then we'll talk about issues with risk, which include ignoring a risk, summing median values, most likely, or even median values. It's often the case that we sum median values. Talk about what that is and why that's a problem. trouble with the triangular distribution, why the normal ain't so normal when it comes to cost estimating, and ignoring correlation. Why focus on mistakes? So let's have a little history here from the sport of tennis. So John Ramo, who is the R in TRW, so back in the 1970s, he wrote a book called Extraordinary Tennis for the Ordinary Player. And one of the things that he noticed in his own playing as an amateur player at the club level was that he made a lot of mistakes. And he looked at this analysis on the statistics, being the kind of engineering background that he had and quantitative background. He decided to do some analysis of this, and what he found was that the professionals, that 80% of the shots in professional level tennis were decided by a winning shot. Whereas at the amateur level, it's just the reverse. 80% of the points were decided by a mistake. You notice that, looking at it and thinking about it, that the tennis court is set up for really good players to hit incredible shots, not so much for ordinary players. So the best way to improve as an ordinary player is actually to try to make fewer mistakes and focus less on hitting winning shots. As the economist Hyman Minsky once said, in order to succeed, we have to know how to avoid the most likely ways to fail. So, we can become better at cost estimating and develop better cost estimates by making fewer mistakes. Okay, let's go into the first one, which is abusing averages. An average, I think most of us know what averages are. An average is just a number that represents a central or typical value in a data set. Some common types of averages are things like the mean, the mode, the average, the mode being the most likely value, the median being, the midpoint. If you're talking about a highway that's got two lanes on each side, the median's in the middle, the kind of the middle point between those two. And then the mean is just the sum of the numbers divided by the number of numbers. And there are two different types of means. There is the simple mean, which is just averaging the numbers and then dividing by the number of numbers. And the other one is to weight the mean based on how prevalent it is within a subset. Some common misuses are to use a simple mean rather than a weighted mean when you should be using a weighted mean. And I'll provide an actual example where that has happened in the past. Another misuse is to use a mean represent skewed data. Despite skewed data, it's better to use the mean and the median when you have skewed data in cost estimating for summing cost estimates with a WBS rate. So next, I want to talk about and dive into the details of a weighted mean versus simple mean example. So here's an actual example. I'm taking all the names off of this program and who worked on it to protect the guilty. There were four programs, and there were several subsystems that people were looking at. And there was a ratio of the non-recurring to the recurring costs. And the non-recurring is the cost to develop the system. And the T1, the first unit cost, is the cost to manufacture the very first unit. And so usually that ratio is typically greater than 1, sometimes less than 1. Just depends on the amount of heritage and reuse of hardware from previous programs. So for the first subsystem that was considered, the ratio was 0.76, 13.6 non-recurring to 17.9 T1, so 0.76. The other ones, it's all a little bit above 1. And if you look at the total, which is the weighted average, which is the sum of all the non-recurring costs divided by the sum of all the T1 costs, that's 0.92. The simple average is higher, it's 1.21. In this case, you need to weight these by the actual amounts to get the correct ratio, because if you're taking together what the total is, you need to take into account how much each one contributes. And that's the weighted average. What was done for the cost estimators when looking at the non-recurring to T1 ratios, they actually just calculated a simple average, which was incorrect. They should have used a weighted average. Next, let's talk about another example of skewed data. So someone that's been in the news a lot recently is Elon Musk, who is currently, I think I read today that he's worth $251 billion. He's had a back and forth on Twitter with Elizabeth Warren about not paying taxes. Apparently for 2018, he did not pay any taxes because he does not take a salary from Tesla, but he has stock options. And so he did point out that because he's concerned that tax rates are going to go up, he's going to exercise his options, which means he's going to pay taxes. He's going to pay a lot of taxes. He may pay more taxes than anyone's ever paid in the history of America. So the point being that with net worths, what's the average may not be so average. Depends on who's in the bar. So let's say there's 5 people that walk into a bar and you look at their net worths, and one is worth $50,000, one is worth $200,000, one is worth $500,000. One has a net worth of $1 million, and then one has a net worth of $100 billion. So an Elon Musk or a Jeff Bezos, someone like that. What is the average net worth of these individuals? You take the mean, the average net worth is 20 billion. Would you consider 20 billion to be representative of the group as a whole? Well, not so much, but the median is 500K, and that probably is representative of the group as a whole. If you were to put 200 people in a bar, we have a similar type thing. The person that made with $100 billion net worth would totally dominate the mean, and the mean would be skewed. So even if you had 100 people in the bar and they all had the rest of them had zero net worth, and one of them had $100 billion net worth, the average net worth, the mean net worth of the entire number of people in the bar would be $1 billion. Very unrepresentative of the bar as a whole, right? Pretty much everyone in the bar is a pauper, except for one person. So when the data are skewed, the median is typically a better representation of the average or central value than the mean. However, when it comes to cost estimating, and we're estimating in the work breakdown structure, and then we're adding together things, typically cost is skewed. We'll talk more about that later. The normal ain't so normal. The mean is a better choice. And the simple reason is that you can add the means. The sum of the means is the mean of the sums. And if you add medians or other values below the median, like the mode, it will lead to underestimation. And we're going to talk about more about this later. This is one of the issues with the risk. We'll talk about the misapplication of parametrics next. When we look at parametric models, which are also called cost estimating relationships, or CERs for short, they're based on a certain level of data, either at a subsystem level or component level, maybe at a piece part level, or even sometimes at a very high system level. These things are typically nonlinear. These types of equations typically are nonlinear. Most of the ones that we work with in defense and aerospace are nonlinear. There's typically some sort of economy of size going on. So it's typically a nonlinear type of thing, unless you get into very small things, or things that have very limited amount of range in them. But many of the things systems we work on, if you consider spacecraft, these range in terms of size, they range from the very small CubeSats all the way to large systems. It's typically the case with other systems as well. If you look at aircraft, missiles, you have very small missiles, you have very large missiles. So these range in terms of their differences in terms of orders of magnitude. And that is both the size, the scope, as well as the cost. And so in such a case, it's typically that you're going to have a nonlinear relationship because of the economies of size, and just because when you're looking at how to estimate these kinds of things, what you're really concerned more about, if I have a $1 million spacecraft versus a $1 billion spacecraft, I'm more concerned about, am I within 10% versus am I within $5 million of the actuals, if my estimate within 5 million of the actuals. Now, you wouldn't typically say that for these large ranges. You would typically be more interested in, am I within 5, 10, 15, 20% of the actual costs? And that's going to be a nonlinear type of equation. Application is, the impact of this nonlinearity is that if you develop a CR at one level, it will lead to an error when you develop it at another level. So I'll give you an example of this on the next slide. Now, I found this is another thing I've seen at work. I used to work on a parametric model called the NASA Air Force Cost Model. And I would provide the updates, and the government customer would, and other people would use this software, but the government customer that I was directly supporting had developed an estimate, and was looking at the estimate and noticed that they had taken a CER that I had developed at the subsystem level and then applied at the component level. And I knew the CER was nonlinear, and started looking into what the implications of that were, and sort of applying it at a different level. And it's going to lead to overestimation in this case. So suppose, for example, we have a CER, and the CER is basically the input that you have, such as the weight of the system, and you take the square root of that. that's your estimate. So if the subsystem weight is 100, then your estimate is the square root of 100, which is 10. But now let's say we apply it to two, we have the subsystem weight of 100, but now we apply it to two 50-pound components. So the correct subsystem estimate is $10. But if you apply it, you take the square root of 50 and then take the square root of 50 again, and then you add them. So the square root of 50 is around, it's a little bit more than 49. Square root of 49 is 7. So 7 plus 7 is 14. So when you take square root of 50 plus square root of 50, it's roughly $14.14. So it's 40% greater. So we were seeing these large overestimates because of this misapplication. If you have to do it, if you have to actually use this kind of equation at a different level, if you're really trying to model a lower level, you can apply a component correction factor. So the component correction factor is CCF, which is P raised to the 1 minus B, which P is the component weight as a percent of the subsystem weight, and the B is the weight coefficient in the subsystem level CER. So that will help correct for that. It will help you avoid overestimating if you have to do it. If you can not do it, just go ahead and model the system at the same level that the CER was designed for. Next issue we're going to talk about is the curse of dimensionality, which has multiple implications. And the graph that's there on the right, you kind of see that, okay, if I have four in one dimension there, and now I have X and Y in 4 dimensions, and that's 4 squared 16. And now I've got X, Y, and Z, and they're all 4. 4 times 4 times 4. That's a much bigger number, right? So you go from 4 to 4 squared to 4 cubed. So you go from 4 to 16 to 64. And the idea is that what this illustrates is that as the number of features, as the number of inputs, as the number of variables that you want to model, as that grows linearly, the number of data points needed to model them grows exponentially. We have big data dreams, but small data realities. So, in this era of big data, many of the things that we're using for parametric development are small. The bigger data sets that I've seen have been on the order of hundreds, sometimes for software. I've seen a software maintenance data set that's been in the hundreds, and there's an Army, there's a DoD data set based on they've collected for SRDRs, the software requirements, data reports that are in the hundreds. But the next biggest set I've seen is like for satellite spacecraft, I've seen in the dozens, maybe up to 100. If you get to the system level, like Joe Hammaker's quick cost model, it's over 100 data points, between 100 and 150 data points. But most of the time, it's even smaller than that. When I was working missile defense, they're trying to model kill vehicles, which are a small specialized piece of equipment. There's only a handful of those that are directly, directly been modeled or been developed. So it's really have a small data set. And I went to a talk a couple months ago where a data scientist said that he would cringe if he had a data set that was less than 1,000 data points. So most of the work that we're doing and the data sets we're analyzing are very small. We have to be careful. Be very careful about applying parametrics to small data sets. It can lead to overfitting. It's an overlooked problem in cost estimating and statistics in general. If we really only had access to the true signal, because the data we work with have some noise in it. If we had access to the true signal, we would not be misled by the noisy data, but we can only see the noisy data. So here's an example. When the Space Shuttle Challenger blew up in 1985, 86, there was a ripple effect throughout the spacecraft industry. The space shuttle was used to launch satellites. It was going to be used to launch Hubble, for example. And because of that, these satellites that were planned for launch on the shuttle they had to find other rides to space, or they had to be put into storage for a while because really there wasn't another good option for the Hubble except for the shuttle. So basically they had to take the Hubble and put it in clean room storage, which is expensive. It can cost millions of dollars a month for clean room storage. You can't just put these things into room closets. So there's a ripple effect. There were things, the Space Shuttle Challenger caused some cost increases for a variety of different spacecraft. But the problem is we can't really model that, right? So there's some noise in the data in the sense of that's something that you can't really include. You can't include a Space Shuttle Challenger accident variable in your model because you don't know when those are going to occur, when those are going to impact. It's not a repeatable phenomenon. So in the real world, we have to work by induction. So we have to infer the structure of the data from the available evidence, which is something that Nassim and Taleb pointed out in Full by Randomness. So we are most likely to overfit a model when the data are limited in size, which is often the case with us. The data that we have, the data are noisy. All our data are noisy. There are other things that impact us. There's a government shutdown can impact it, labor strikes. There's all kinds of different things that can randomly impact that. And also when your understanding of the fundamental relationships is poor, and I will argue that to some extent that in cost estimating, when you use parametrics, we're using things like weight and size, lines of code for software. Those are not necessarily the things that truly drive the actual cost of the system, but they're sort of proxies for the scope. So when it comes to cost estimating, we don't necessarily have a good grasp of the causal relationships between what is it that's really driving the cost. So we are subject to that third point as well. Okay, here's an example. There's a strong correlation between the variables displayed in the graph, right? So the R squared is 73%. That's pretty good, right? It's only 10 data points, but really a strong connection between the two variables, right? The awful truth is that I generated those data at random. So when you have 10 data points, you can see things like that, even if there is really no relationship between the variables. Those kinds of patterns are easy to find in small data sets. So typically what you would see in a large population, like we have here on the right, the large population of data points, it is possible to pick out where there's no relationship, it's basically a scatter shot. R squared is basically indistinguishable from zero. It is possible to pick out a subset of the data points that's small, where there is a strong trend, right? Almost 100% correlation between the data points that I've kind of highlighted there. Okay, so this is about the law of small numbers. So there's a tendency to try to infer patterns from very small amounts of evidence. Unfortunately, these small samples are not likely to represent the overall population well. The psychologist Amos Tversky and Daniel Kahneman term this phenomenon the law of small numbers. People's intuitions about random sampling is that the law of large numbers applies to small numbers as well. And Tversky noted that in the testing of hypotheses, psychologists tended to derive more certainty from the data that exists. And so we have the same tendency when we look at cost data and developing parametric equations. How do we deal with small data sets? Your traditional regression analysis is designed to deal with data sets that have at least 50 data points. So if you have a small data set, which is often going to be the case, you can, here are three things, there are other things to look at too, but here are three things that you can look at. You can impute. Imputation is a statistical method for filling in the gaps in your data set by using some statistical methods. Kind of educated best guess to a certain extent, but it is based on statistics and the overall structure and the correlation of the data. So it allows you to use all the data that you have. You can estimate at a lower level. So you may have not that many guidance, navigation, control. We don't have that many kill vehicles, but if you break apart a kill vehicle and when you look at the propulsion system, reaction control system, there are more reaction control systems that are out there, and the same types of ones that have been used on kill vehicles are used on other things. So there is a bigger data set at the component level once you break down the components. Another type of thing that I like is Bayesian techniques, which allows you to use all your data, both the subjective data and the objective data. Subjective data includes your experience. So you might have some notion. So what might give you some confidence, small data sets, you might have some notion is that there's a relationship between the weight and the cost of a system. You've seen it over and over again. You have a small data set, you derive a CER, and it kind of fits within the framework of what you expect to see. That gives you more confidence. You can also use that in a mathematical framework to actually derive the CERs. And if you're interested, I can give you references on that. I've written a paper on that. And I've got an example that I can provide on that. Okay, and then another way that people tend to overfit is they only look at the training set. So it's often the case that when you do validate, you would take, if you have a large data set, you would take 2/3, you would train the model on the larger data set. So the coefficients will be fit using the larger data set. And then the other 1/3 we use for testing and hold out and to see how well it fits. we often don't have that luxury because of small size of our data sets. But if you were to do that and you were to train the models, what you would see is that as the model becomes more complex, the green line would decrease as well as the training line. The training line is always going to decrease. You can never make it worse by adding in more variables. You're always going to increase your R squared. You will likely increase your standard error, even though you lose a degree of freedom every time you add a variable. But as your training error is likely to decrease as you, no matter how complex you make the model. But at some point, the validation error, it will start to decrease as you add variables. And at some point, it will bottom out and start to increase. You'll start overfitting. This is where you become a sweet spot here between underfitting and overfitting. When you have the simplest kind of model you can think of is just take the average of the data set, don't have any parameters, and use that. Then you're likely underfitting. So you're over here on the left side of that curve. And then as you add a variable, you move to the right a little bit. Your generalization error will likely improve because you now have a model. You are reducing the amount of underfitting that you have. But at some point, you're going to start fitting the parameters to the noise in the data, and then the training error will creep back up. The testing error will creep back up. So you have to be careful about that. You tend to try to do that. Now, given that you have small data sets, you like to have small data sets. What is the way around this? The way around that is cross-validation. So this splits the data into this partitions the data into multiple subsets. So you might say 5 or 6 equal subsets. So 5-fold cross-validation. Let's say at 100 data points, you would then group those into groups of 20. So you have 5 different partitions of 20 data points each. And what the cross-validation would do is you would fit the data to 80 of those data points, and you're holding out 20 at one time. So you fit to 80 data points, calculate your goodness of fit statistics, your R squared, your standard error, et cetera, on the 20 data points. And that would give you one fold and what the fit is for that one fold. If you then repeat that, you do it 5 times, you hold out 20 data points at one time and you fit to the other 80 and then test on the other 20 that you've held out. You do that 5 times and you kind of take the average. That's the cross-validation. The advantage is you can save more of your data for the training. So every data point has an influence on training the parameters, but you get the advantage of trying to getting better generalization error as a result. Okay, so that's cross-validation and the recursive dimensionality. The other category of mistakes we're talking about today involve risk analysis. The biggest one of those is ignoring risk. Projects of all types have significant cost and schedule risk. Unfortunately, it's often ignored. And the graphic that's there is the Hunt Linux globe. Is one of the oldest still in existence. It's a small copper globe. It sits in the New York Library in their rare book section. It has the phrase Hic sunt draconis. It's Latin. That means here be dragons. It's inscribed near the coast of Asia. It indicates there's risk in uncharted territories. So medieval cartographers recognize the importance of risk. But many times project managers have forgotten about that and often ignore it. And even when quantitative risk analysis is conducted, it's often prone to mistakes. And we'll discuss some of these. So this is about the amount of risk that's out there, making sure that you recognize that there is significant cost and schedule uncertainty. If you ignore risk at your own peril, projects of all types have a significant amount of cost and schedule risk. So I wrote a book about risk management last year, published by McGraw-Hill, and my background is in defense and aerospace. So in pitching my book to McGraw-Hill, my initial draft was heavily focused on that. And they said, well, that's great, but it's too narrow, and we'll publish your book, but you've got to broaden your focus and look at more projects. So I was able to do that and found that the kind of work we do is the risks that are there are not so different from other types of projects. Even roads, regular experience, cost overruns, you think a road would be pretty simple, but the average cost growth is a little lower than NASA and DOD, which 20% versus 52%, but really not the worst. We're not the worst, not the best. We're kind of right in the middle of the road. We're not that far out of the typical software and IT type of cost growth we see, and we're much less than the Olympics, which is a poster child for cost growth. These kinds of things are common, they're frequent, they're high, and they can be extreme for costs, which can, doubling or more in costs. You want to call it extreme cost growth. And it can be, if you look at, for example, James Webb Space Telescope, which still hasn't launched. NASA initially wanted it to cost $1 billion 25 years ago, and now costs more than $10 billion. The cost is still growing. They've had some issues trying to get it launched. So a lot of issues there. What this means is there's a lot of risks out there, and it's not managed well. Okay, I'm going to talk about some specific issues of risk analysis, some of the median. So this is a notional example. Not too dissimilar from an actual example I looked at when I was at the Missile Defense Agency. At that time, the agency policy was to fund to the 50th percentile. And then I looked at what the risk analysis was for the individual projects that we were funding to the 50th percentile. And then I aggregated them, and I saw that the overall confidence level was at the 36th percentile, 35 percentile. So this is very similar to that. If you fund below the mean and you start adding the means, you're going to be lower than the overall mean. And in this case, just this notional example of 6 projects, we're at the 36% confidence level. That means even though each individual project, there was a 50% chance of an overrun occurring if these are truly accurate risk analyses. When we aggregated them, the overall agency level, if you had 6 projects in an agency, the overall organization or agency's confidence level would be 36%. So you made things worse by funding at the 50th percentile. At least if you funded the mean, you would be able to offset overruns with underruns. And you expect that the cost to grow by 12% for the portfolio just by funding to the median. You're setting yourself up for 12% of cost growth, assuming nothing else really bad happens. So you need to fund to at least the mean when you look at projects. And you also, if you look at a WBS level and you're aggregating your estimate, you need to, at the very minimum, aggregate the means of the estimate and provide an overall mean. The next thing I want to talk about is an issue with triangular distributions. They're very simple. You only need a low, a most likely, and high. So it's kind of easy to use with expert judgment if you get someone to elicit and provide a low, a most likely, and a high. That would give you 3 inputs, and you can do risk analysis. The big drawback is there's no tails. You need to have absolute balance. So you can't really incorporate the dragons of risk. The proper use is commonly used for CER input uncertainty, but you still get underestimate some certainty when you do that. The best use is when you're confident about that the uncertainty will not exceed specific bounds. So you have a civil servant salary and you're projecting them out 1 year in the future. You can have very specific bounds on what that could be. That's something you put that on. You have to be careful using triangles and try to use them sparingly, only when they apply. The normal, be careful about using the normal. The normal ain't so normal when it comes to cost estimating. It's why is it called normal? It's also called the Gaussian distribution, but it's the most widely distribution used in statistics. If you've taken a statistics class, you probably encountered this. If you encounter nothing else, you probably encounter the normal distribution. It captures a limited variation, but it occurs in physical reality a lot. The lifespan of humans, that sort of thing. So it's commonly used by actuaries in life insurance, for example. The central limit theorem is often used to justify the normal distribution. When it comes to cost estimating, the assumptions don't really hold. There's several assumptions that don't hold. One is that these things are all independent. Typically, things are correlated when in cost estimating. Even at the WBS level, there is in our assumption is limited amount of variation. Well, there's quite a bit of variation, and so the amount of variation is so high, and the interdependencies are large enough that the central limit theorem really does not apply. You also need a lot of WBS elements. Oftentimes, you don't have that big a WBS. So those 3 factors, you need a lot. You need limited variation, and you need limited or no correlation. And those 3 things really don't apply enough to get the central limit theorem. The log normal is a better choice. So the joint agency, which is the Department of Defense services, the Army, Navy, Air Force, the Missile Defense Agency, and NASA, a joint cost uncertainty handbook recommends using the log normal as a default. Another issue is ignoring correlation. So if you ignore correlation, which is a tendency for cost risk to occur in tandem, when structures increases in cost, thermal control also increases in cost because, so for example, if your structure gets bigger, then and you're using thermal coating, you're going to need more thermal coating, so the cost will go up. However, it's often ignored. It's easy to overlook or ignored. So I would pick to leave it out. And even if you don't want to make a decision about correlation, if you decide not to include it, you still made a choice, to borrow from the old song. The impact is you dramatically underestimate the total amount of risk. So as measured by the standard deviation, in a 30 element WBS, assuming no correlation, when it's actually 20%, will underestimate risk by 60%. So it's a famous chart that Steve Book put together around 30 years ago. And even when you are using the knee in the curve method, you can still be underestimating the amount of correlation that you need to include. So we are likely to be wrong in our assumption of correlation. We don't exactly know what the right correlation is most of the time. The knee in the curve will tell you how much you underestimate the standard deviation, but it won't tell you how much you're underestimating it by assuming it's 20% when it's really 60%. So if you want to try to use a robust approach where you minimize how wrong you can be in practice, 60% is a better value because you're gonna be less wrong by assuming 60 by and large than if you assume 20. So that's what that curve tells you. Okay, so we've talked about several things throughout this presentation. Kind of want to summarize and hit the key points again. We've talked about abusing averages. Be careful about using simple means when you should be using weighted means, and vice versa. The skewed data, be careful and make sure you use, consider the impact of skewed data. If you're using skewed data and you're not really adding it to anything else, you're just using it as its own standalone thing, then the median is better than using skewed data. If you are adding things together, even if you have skewed data, it's better to use the mean because the means add. When you're using parametric equations, you want to try to apply CERs at the level at which they're developed. If you use component level CERs at the component level, use subsystem level CERs at the subsystem level, or apply a correction vector. You need to kind of understand what the underlying equation is, though, to do that. The curse of dimensionality, which is the tendency to overfit in the presence of limited data. If you over-optimize to training sets, can lead to poor predictions in practice. Recommendations are to use simple models, don't overfit. Use imputation to fill in your gaps, model at a lower level, and use Bayesian techniques. And also, to avoid overfitting to the training set, use cross-validation. Risk. This is the dragons of risk. We need to make sure that we don't ignore risk. We need to make sure we do risk analysis. Don't sum median values, sum the means. Use the triangles and normals distributions appropriately. Make sure you include correlation. So some recommendations is, do this right. And to help do this right, you can also read my book. So there's a little bit about my book. It's available now from Amazon, Barnes & Noble. You can read chapter 1 for free if you're interested in a sample. And there is an audio version that's out now available as well from Audible and audiobooks.com. And so I guess I'm going to turn this now over to Q&A.
All right. Thank you, Dr. Smart. And thank you, everybody, for joining us today. We value and appreciate the privilege of your time and attention this morning. So please use the question and answer button at the bottom of your screen to ask the questions you have during this period at the end. And also, I want to remind you that video of this session will be available by Friday at galorath.live. So before we dive into the live Q&A, I want to let you know also that we have dropped a link to the post-event survey in the chat. So if you want to hover at the bottom of your screen to see the chat window, click on that. The PDF version of today's presentation deck, among some other handouts, will be available at the end of that 2-minute survey. Also during the Q&A, we're going to use the upvote function, not the raise the hand. So that way you can upvote the questions that are relevant to you and you don't have to retype them all in. So with that, I'm going to go ahead and open up the Q&A portion. So please enter your questions in the Q&A. And let's see. Okay, first one. What is a good number of data points to use? And then also,
Okay.
what is the validation process for CER when using fewer data points?
So the best practice, if you're using regression analysis, the best practice, if you're just doing standard traditional regression analysis, you're not using a Bayesian technique, then simulation studies have found that you need about 50 data points to fit one variable. And basically you have a high confidence level that basically you're not just fitting this random noise. And then for every additional data point you want to use, you need another 10 data points. So if you want one variable, 50 data points, you want two variables, you need 60 data points, you want three variables, you need 70 data points, so on. So that is what standards frequentist statistics, traditional regression theory would tell you that you need. If you have fewer than that, you would try to lean on Bayesian techniques, use some experience, use some judgment. It doesn't necessarily have to be subjective. If you have, for example, some prior knowledge or a prior study that's been done that has analysis is based on, and you lean on that as your prior, and then you do some limited amount of analysis with the smaller data set that can form your likelihood, and you can combine those two to get a better equation. But traditional regression analysis say at least 50 data points, and that's based on those simulation studies that I mentioned. Another question, a good question, Justina. So the next question is also from Justina, is what is the validation process for CERs when using fewer data points? If you're using fewer than best practice, typically any kind of CER that you would develop, if you do an estimate based on that value, it would be good to compare it to some sort of cross-check, especially when you have limited data. If you've got some sort of cross-check, if there's some sort of historical system that, so if I do an estimate based on this and the estimate comes up to be $30 million, and I have an historical precedent that's not somewhat dissimilar, somewhat similar to this system, and it costs $50 million. Okay, well, maybe you're in the right ballpark. At least it's not an order of magnitude different. If it were $40 million, it'd be even more confidence, right? But so that would, and if you could also justify, for example, if it's really true, you shouldn't try to force fit it, but if it's really the case that, okay, well, it's $50 million, but the system that we're estimating is actually going to be similar, and there are some valid reasons that you can assume that. You say, okay, well, historical precedent would say 50, and now our equation is saying 30, but it's simpler, then that could help justify that. So finding some sort of historical cross-check, another equation that's out there, another study that's been done to help cross-check or validate, expert judgment on those kinds of things. Anything that you can rely on like that, that you can help provide. Erica Cadner asked, did you encounter standard data sets in defense aerospace? I often have single-digit data sets. So yeah, so missile defense mentioned that kill vehicles talk about 5 data points, so it's very limited. NASA type projects or spacecraft projects, we developed a new SEER model in the last few years called SEER for Space. That's based on about 50 data points, so it's right on the hairy edge of the standard statistical theory. So we do have some. If you look at satellite spacecraft, you can find them in the dozens. Typically, they're similar enough, and that you can kind of lump them into a data set. If you get really picky and you say, okay, well, we can only use planetary spacecraft that launched in the last 5 years, then you're going to really limit yourself. If you can kind of relax your constraints on that a little bit, and say the last 20 years, and you allow both Earth orbiting and planetary in the same data set, you can widen that a little bit. So if you kind of relax your constraints a little bit, if you think, well, these are not exactly the same, but they're similar enough that they would have similar statistical trends between, say, for example, weight and cost, then you can use those. But yeah, single-digit data sets, they're not uncommon. That's where you would try to lean on, some Bayesian techniques. If you've got, and also, so this, for example, for example, if you had an equation that is your cost is equal to some constant A times the weight raised to some factor B. Now, what is the B value? The B value gives you some sense of the economies of scope or size or scale. And you can kind of get a handle on that using judgment. if you think that for software, the answer is there are often diseconomies of size. So that number is often 1.1, 1.2. But for hardware type systems, that number is somewhere between 0.5 and 0.9. 0.5 more structural type items, 0.7, 0.8, and more electronics. So you can start at that point and use that as sort of your prior, and then update that with the data set that you have, and then that can provide some more accurate answers.
Very cool. Another question, Christian, is what is the best way to connect system requirements to system cost?
Well, the card should be a good way. That should be the documentation on the system requirements. Using parametrics, looking at historical data on the requirements and trying to get those to cost. There's an emerging science that has been not very applied very much to cost estimating called causal analysis. And, doing some analysis based on that would also be a good thing for people to do in the future.
All right, thank you. Can you implement cross-validation in Excel?
Yes, it's a manual process in that case. It's a little slow, but I've done it. If you can use something like R or Python, there's a lot of tools that'll do it a lot faster. So, but you can do it in Excel.
Okay. Another question. What are some good techniques for using imputation to fill in the holes in data sets?
Yes. Some good techniques. There's something called, there's two sort of standard techniques. Expectation maximization is, which kind of helps you develop an equation without actually filling in the hole directly. But it basically uses all the data points, even the ones that have holes. That's expectation maximization. And then another one for actually filling in the gaps in the data and that you can then do analysis on is called MICE, multiple imputation by chained equations. Chained equations is a type of Bayesian analysis. So those are two, expectation maximization and MICE. I see there's some other things in the chat too. There's a couple of questions in the chat. So any further details about the presentation available in the book? Yes, the book does, when it comes to risk analysis, the book does have that. For the other things like averages and misapplying parametrics, there are some handouts that are available that all the attendees will have access to download. That other papers I've written, including white papers and presentations and other things that go into some of the details about those topics. So those are some references. I guess Adam provided that. And
yes.
And there was also something up above about an international EPCM insists on using the cumulative distribution, so P1, P10, P90, and P99 for all cost variable inputs into the QRA models. I think it's very, very hard to realistically assess the P1 and the P99. You might be able to get the P10 and the P90 for all the inputs. I would think that would be very hard to really realistically assess the P1 and the P99 for all the inputs. I think that is asking for too much.
Okay. All right. I think that's all the questions that we've seen come through then. So if you have more, of course, you can always email us with any further questions. And please remember to click on the exit survey, the link in the chat window. Adam has posted it in there. You can provide feedback on today's session and suggest topics for upcoming sessions. You'll also be able to download today's presentation and also enter to win a $100 Amazon gift card. And please check Galorath.live for the upcoming January webinar for that information and any other updates, etc. So I'll keep the webinar window open for a moment more so you can have time to access that chat, the survey link, and it will also be emailed as well if you miss it today. And then once again, I want to thank you for attending and for everyone to have a wonderful day. So we'll keep that open so you guys can click on the chat link just another moment or so.
If you want to ask me questions outside of this venue, I mean, I'm on LinkedIn. You can find me there. You can also contact me directly. I'd be glad to connect with you.